Hello, I hope you're having a lovely day. What is preemption? What is a preemptive kernel? Are there really four different ways of doing preemption? These are some of the questions that we will be answering in the next 30 minutes. I'm your host, Giovanni, from the performance team at SUSE, and this is SUSECon Digital 2023. This is the list of the different types of preemption that are available in the SUSE Linux Enterprise kernel. The list that gives the title to this session. They are none, voluntary, full, and preempt-RT. None is the first one we will study, and with preemption none, there is no kernel preemption. Kernel preemption refers to the possibility that kernel thread are interrupted and replaced by some other thread in kernel mode, kernel preemption, that are more urgent. Preemption none is the default setting in SUSE Linux Enterprise Server, as it is suited for server applications. Having more preemption implies having more context switches, and generally server workload favorize throughput. The second one is voluntary, and with voluntary, the kernel is preemptible to some degree. There are explicit scheduling point, invocations of the scheduler, a few hundreds, that are inserted throughout the kernel. This makes voluntary more responsive than none because threads have to wait for a short amount of time before being executed. Then full kernel preemption, which makes the kernel fully preemptible except for critical sections and interrupt handlers. And the target usage of full preemption is desktop systems, where applications are interactive and need to respond to user input quickly. Then we have the kernel we find in SUSE Linux Enterprise Real Time, which is based on preempt-RT. And at this fourth degree of preemption is more preemptive of all the others, but the focus is not on having an average low latency, rather a bound on the maximum latency. Real-time applications can tolerate being having an average latency which is maybe not so small, but cannot absolutely tolerate peaks in latency. And this is what SUSE Linux Enterprise Real-Time focuses on, a bound on the worst case execution time, which makes this operating system suitable for real-time applications. If you're not familiar with the schedule, with the Linux kernel internals, let me introduce the schedule function, which is the entry point for the task scheduler in Linux. Calls to this function is how a thread can replace another on the CPU. So preemption happens when the function schedule is called. If we want to have more preemption, we need to call the schedule function more often. Compare this with user space applications where you have no idea if your code is being interrupted and resumed later. This is all abstract away. But in the kernel source code, the context switch is very explicit and happens by means of calling this function, invoking the scheduler. Let's define preemption. Preemption is the act of interrupting, of suspending a thread on the CPU, a thread which is executing, and replacing it with another thread, which is more urgent. And the way we increase preemption creates more opportunities for context switches, which make thread wait for less for their time to run on the CPU. Scheduling latency is the central concept in this discussion about preemption. We increase our preemption degree because we want to reduce scheduling latency. And what is it? It is the time between that a thread which is ready to execute needs to wait for an available CPU. We have here a conceptual representation of the states a thread can be in. So let's look at the possibilities. There are those green boxes which are represents a thread that is running, that is executing instructions. And this can happen in kernel mode or user mode. We call such threads on the CPU. They are on the CPU, they are running. But there are also threads which are not running, they are sleeping, and those are the purple boxes. Threads can be, for example, in those situations, waiting for a resource. A thread could stop executing because it needs some I/O from the disk or from the network, or it is waiting for a lock to become available, or it's waiting for some work. So those threads have left the CPU because they needed something. But there is another state, which is this state here, runnable, which represent threads that are ready to run. They are not waiting for a resource, but are not running yet. So scheduling latency is the time between a thread enter the state, the runnable state, and the time it is scheduled on the CPU. Note how thread can leave the CPU because they wait, they need something, or throughout this other arrow, which I have labeled preemption, because the scheduler replaced them with something which has a higher priority, something that is more urgent. So this arrow here, preemption, is the one that we are studying here in this session. We know we have a definition for preemption. We know that what is a scheduling latency. We know that the scheduler selects tasks based on their priority. So now let's talk about the priority of tasks. What is it? So when you run your application, your user space application, you can choose which scheduling policy should apply. Scheduling policy, if you don't, there is one that is assigned by default, which is a sched normal here. So scheduling policy have all, each of them has a different behavior. But what we want to see here is this hierarchy of classes. The scheduling policies are those here in all caps letter, and they are grouped into three classes. Earliest deadline first, real time, and completely fair. So what we need to know about the classes and scheduling policies is that EDF, the first one, is the class with the highest priority. The tasks here have the highest priority. Real time comes right after, and last we have the completely fair class. Within each class, Processes are also assigned a priority, which you, the user, decide. And in EDF, tasks are organized by those three parameters: runtime, deadline, and period. In real time, we have a number between 0 and 99. And in CFS, we have nice values. So we have this higher level hierarchy of classes. And within each class, we have individual priorities between tasks. We have mentioned priority, we have mentioned preemption. How do we connect those two ideas? Well, preemption is a mechanism to honor priorities by means of creating more context switches for higher priority tasks to be executed. We now start studying all the individual flavors of preemption, and the question that we will always ask is, where is the schedule function called? We know that the schedule function is how we create preemption. So we want to know when is and how often is this function called. We begin our exploration with none, so the case of no kernel preemption, which is the default in SUSE Linux Enterprise Server. Schedule is called upon return from a syscall, so return to user mode, and return from an interrupt handler to user mode. This diagram on the right illustrates the first case. There are two processes, this ribbon here on the left and then the other one on the right. Lower priority, higher priority. The colors represent their execution stages. Gray is for user space in this illustration. Low priority process is running in user space, invokes a syscall, and when the syscall is about to return, we have a context switch because the schedule is invoked. And as we can see, there was another process that was waiting, color white, had been waiting for a while. It is higher priority, has accumulated some scheduling latency, but now upon return from the syscall, which normally would have returned to this process, this very same process that called it in user mode, but schedule is invoked and we have a context switch and our high priority process run. This is a slightly different scenario, but similar. It represents the second occasion of scheduling in no kernel preemption regime, which is when an interrupt handler terminates execution. So we have a process in user mode. We have an interrupt handler that would return to user mode, which is the condition, return from an interrupt handler to user mode, not to kernel mode. Here we would return to the process that we just interrupted, but at the end of the interrupt handler, the schedule is invoked. And we notice that there was a higher priority process waiting, so this is selected. This preempts the other process. These are the only preemption opportunities when there is no kernel preemption. So when we return to user mode from a syscall or from an interrupt. Be aware that if the interrupt, like in this other third diagram, occurs in kernel mode, no context switch happens. We return to the original process. So the interrupt handler must return to user mode in no kernel preemption. Then voluntary preemption, which can be selected at boot, as we see here, consists in the addition of explicit scheduling sites that I have represented here with the red sticks. This is our low priority process, syscall, explicit scheduling point from voluntary. Another process is now in the picture, and as soon as the first process reaches the scheduling point, the scheduler will check if there is anything else to run. In this case, there is, and it is executed. Note that with voluntary preemption, the scheduling opportunities that we saw with previously still apply. Those are additional scheduling points. The last preemption mode available in SLAS, in SUSE Linux Enterprise Server, is full kernel preemption. The kernel is preemptible everywhere except for critical sections, which is a spin lock is held, and interrupt handler during the execution of an interrupt handler. The additional scheduling opportunity is when an interrupt handler returns to even to kernel mode. So this is the application of the kernel is preemptible everywhere, because interrupts can happen everywhere. And so upon the returns of the interrupt, wherever it was, except for critical sections, spin locks, regions, we can invoke the scheduler. And again, this curly brace indicates the scheduling latency, and our higher priority task is scheduled. Compared with what would happen with no preemption, where our higher priority task has to wait all the way until the syscall is terminated, including all the interrupts that were processed and fired and processed in the meantime. As I anticipated, the preemption flavor can be selected at boot, since SUSE Linux Enterprise Server 15 SP4. The values are none, voluntary, and full. The default for SLAS is none, but you are free to choose if you want to experiment with the other flavors at boot. Prior to SLAS 15 SP4, the preemption could not be changed. So we used to release several kernel packages with several preemption flavors. The SUSE Linux Enterprise Real-Time is another operating system separate from SLAS, with a kernel based on preempt RT. And the focus, it is more preemptive, so there are more cases where kernel code can be preempted, but the goal is not reach the absolute minimum possible scheduling latency, rather put a bound on what the latency could be. So the goal for the real-time kernel is determinism, not average low latency, but guarantee that the worst case execution time is within a certain threshold. The critical sections now are preemptible, contrary to what we saw before. And interrupt handlers also are preemptible because they are executed in a separated kernel thread. And we also have a way of avoiding priority inversion. We will see now the way that what is the benefit of having preemptible interrupts. There are a couple. The first one is depicted here, and we in this illustration on the left, we have a high priority task which we wouldn't like to be to suffer interference from interrupt, but without the real-time kernel, the interrupt that arrive must be processed until the end, and our higher priority task is then delayed. Rather, with the real-time kernel, the interrupt is fired, but only a small amount of processing is done, just enough to acknowledge the interrupt and wake up the dedicated thread that will run the handler. If our high priority process has set a priority higher than the kernel thread executing the handler, which we can set, and that is the purpose of having handlers in dedicated threads, our process will immediately preempt the handler and can continue execution. The handler will be executed at a later time. The second benefit is in improve the time for interrupt dispatching, dispatching of critical events. On the left, we see the ordinary interrupt implementation, which we could be in a situation where an interrupt that is not very important for our applications, for example, a networking interrupt, if this is not necessary or critical for our real-time application, would delay the processing of an event that we really care about. On the contrary, in the real-time kernel, interrupt handlers are preemptible threads like any other kernel threads, and so the kernel is still receptive to interrupt, and our critical event can be processed immediately. Now, priority inversion is a situation that can happen, and it could be a cause for latency that the real-time kernel can avoid by the solution that we will see now in the diagram. So, how does priority inversion happens? We have three tasks in this example on the left: a low priority, middle priority, and high priority. The low priority task acquires a lock during its execution because it needs to to use some shared resource. The high priority process preempts it because it's high priority, but also needs the same lock, which is not available. So high priority process block and sleeps. Low now runs again, but it's preempted by some third middle priority process, which has nothing to do with our lock, nothing to do with our shared resources, but is there, and it is indirectly delaying the high priority process, which is waiting on low to release the lock. So this is a problem. This latency can be unbound, and priority inheritance consists in when a thread acquires a lock, it will then be promoted to its priority will be promoted to the highest priority of all threads that are waiting on that same lock. So in this case, when our low priority process is scheduled again, it with this lightning graphics, I represent a boost in priority, so it cannot be preempted by some middle priority process. And we continue, release the lock, and give back and switch to the high priority process that can continue with only the necessary delay and not an unbound delay. So this is the last slide of the presentation. I would like to leave you with a consideration on trade-offs. There are two fundamentally. One is if we increase the degree of preemption, we have lower scheduling latency. So why wouldn't we not choose lower scheduling latency? Because this induce more context switches, which take time. And also the CPU cache, if a task is replaced by another, will then lose its data. So there is a cost in responding quickly to all events. So we can have a lower scheduling latency in one case with a high preemption. But if we leave our thread to execute undisturbed for a longer period of time, this may be more optimal if we can tolerate some scheduling latency. And similarly, regarding the real-time kernel, SUSE Linux Enterprise Real-Time, this operating system focus on determinism, and there is a price to pay. For example, we saw the algorithm for priority inheritance that requires some compute, and so in average, you may even have a slightly higher scheduling latency. What you have is the guarantee that the latency won't ever be higher than a predefined threshold. So there is a price to pay, and the choice of preemption always begins with a thorough understanding of the requirements of your workload. Um, so this is the material for this session. Thanks for your attention, and I hope you found this session useful, and I wish you a pleasant rest of your day.